Right. So just as a reminder, what this forum is for and about, this is a continuation of i2x initiative that we started last year. And the goal of this forum is to facilitate understanding and adoption of new and recently updated standards relevant for existing and newly interconnected wind, solar, and battery storage plants. The forum will convene the industry stakeholders to enable practical and more harmonized implementation of these interconnection standards. The presentation of the portion of the meeting will be recorded and posted. The presentation slides will be shared, but the discussion in the second half of the meeting will not be recorded, but just used for just getting feedback and recommended best practices and challenges and gaps and all of that. We're summarizing every meeting in a summary. And the summary of the meeting is not just meeting notes, but also it's trying to capture what are recommended best practices, what are challenges with standard implementation, what are gaps that require future work. And we keep adding this summaries to the same document that is also posted on the i2x first page. So again, leadership team, we have Cynthia Bothwell from supporting DOE Wind Energy Technology Office, Robert Reedy supporting DOE Solar Energy Technologies Office, Will Gorman from Lawrence Berkeley National Lab, Jens Böhmer from Electric Power Research Institute, me, Julia Mativosian from Energy Systems Integration Group, and Ryan Quint from Elevate Energy Consulting. Apart from that, we'll have varying presenter sets for each of the meetings, depending on the meeting scope. So before we get started and talk about the agenda for today, I wanted to open up this polling question. We would really like to understand who is the audience here and shape the future meetings also accordingly. So if you can go to slido.com and enter event code i2x first 2 as a code and just mark what industry you're coming from so that we have a good understanding of the audience. So again, slido.com and event code i2x first 2. All right. So this is a quick summary of the last meeting. Last meeting was just the first meeting in the set, and it was an introductory meeting. We talked about what leads to the need of changing standards and reliability guidelines. We talked about IEEE2800 2022. Standard and ongoing adoption efforts, provided an update on 2800.2 status, and then talked about FERC Order 901 and follow-up NERC efforts that are currently ongoing and resulting in developing of new NERC standards. And then we had a discussion related to these topics. Meeting summary, recording and presentations is posted. And the link is provided here, but we'll also put a link in the chat just in a minute. I will not read through the key themes from the last meeting. You can go to the summary of the meeting and have a look, and also these slides will be posted after the meeting. We'll have one meeting per month. So now we're on the second meeting in the set. And we'll also have 2 in-person events, which will be full-day events associated with ESIG Fall Workshop and ESIG Spring Workshop. And again, this will be in person, but also hybrid events so that people that cannot attend in person can participate. And these full events will be, again, dedicated to topics of changing standard landscape. And again, here below, you can see the link to sign up for all of the future events and the link to follow us on the website where all materials are posted and future meeting details and agendas. So for today, as I mentioned, the previous meeting was more like an introductory meeting. In all the future meetings, we'll start zooming into each of the requirements. And so this meeting is dedicated to write-through requirements. I talked about introductions for today, and then we'll have Wes Baker from Silicon Branch talking about IEEE 2800 Clause 7, which is response to transmission system abnormal conditions. So basically everything that covers write-through requirements in IEEE 2800 standard. Then Jens Böhmer will present a comparison of a draft PRC 29 standard with IEEE 2800 standard. So NERC PRC 29 is a draft that NERC is currently working on as a follow-up on Fork Order 901. And then we'll have Megan Pamperin from MISO, and she'll present on IEEE 2800 adoption efforts in MISO territory, specifically focusing on phase 1, because that is the phase that covered write-through requirements, among other things. We'll have 10 minutes for Q&A and then interactive discussion for the rest of the meeting, and we'll get to those questions later. So now I'll open another polling question. We were wondering for the future, to inform future meeting agenda, if you are interested in a meeting specifically focused on details of IEEE 2800 adoption strategies and ongoing adoption efforts. So basically, without zooming into each of the requirements, we'll rather zoom on each of the areas that are on the way of adoption of IEEE 2800, and they'll talk about the adoption practices and any challenges and solutions that they have. So,
Julia, we might want to wait or just give a second shout out to fill out the first question in the poll. I think there's only about...
That's right. So that's a good idea, Will. I'll still leave the first question open, and maybe as after Wes's presentation, we'll open this one up, and I'll provide a reminder to people before I do. Thanks for that. All right. So yeah, meeting code of conduct, just behave. And we would like to have a good constructive discussion and get some constructive suggestions for the topic of the meeting today. And without any further ado, let's go ahead and get started with Wes. Go ahead, Wes, the floor is yours.
Thank you, Julia. I'm going to share. Just confirming that that's coming through okay?
Yes.
Okay, great. So as Julia mentioned, I'm going to talk about Clause 7 of IEEE 2800 2022. And this is really the clause where all of the details on ride-through capability requirements are housed. I will say it's a very detailed section of the standard. So I'm going to try to hit the highlights, and hopefully the slides are comprehensive. So once you have the slides, you can go into more detail, or you can refer to the appropriate sections. Okay, so in this section, we're really covering both voltage and frequency ride-through. And really what the idea here of the standard is to describe what are the voltage magnitudes and time durations that the IBR will have to ride through. And then once we're in a ride-through mode, what does the IBR need to do? And then finally, once we return to continuous operating mode or normal operations, how does the IBR transition from a ride-through mode back to normal operations? And so before we jump into the details, probably a good idea to just take a quick second to look at some of the different points we'll be discussing. Almost all of the requirements in 2800, as you're probably aware, are applicable here at the point of measurement, which is the high voltage terminal of the main IBR transformer. So this would be basically your transmission level voltage. However, the current injection requirements during a voltage ride through are going to be applicable at the point of connection, which can be thought of as the IBR terminals. It could also be the high side of the IBR unit step-up transformer. The delineation there is basically how the IBR unit is type tested. But for the purposes here, we can just think of it as the IBR unit or the inverter terminals. Okay, so here are the voltage ride-through requirements. If you look at the standard, there's two tables, table 11 and table 12. And I've combined them here into one table so we can kind of look at them together. The key difference here is that the ride-through time durations are different between the two. So table 11 is for those IBRs that have IBR units that may have auxiliary limitations. The example thought of here was IBRs with wind turbine generators, some of the larger motors they may have. And a full explanation of that is in footnote 89. Table 12 is for those IBR plants that have IBR units without auxiliary limitations. So this was more thought of as PV or battery energy storage type IBR units, as stated in note 3. We look at the left side of this chart, it talks about the applicable voltage at the reference point of applicability. By default, that reference point of applicability is going to be the point of measurement. And the applicable voltage is the fundamental frequency phasor component of either the line to line or the line to ground voltage. So some of the results of that, one could think of an example, say, where a three-phase fault, a line-to-line fault, and a line-to-ground fault may all have the same ride-through duration requirements. So that's kind of the implication of it either being line-to-line or line-to-ground voltage. When you look at this table or the corresponding pictorial representation from the appendix of the tables, it should be thought of as a voltage versus time interpretation. And Appendix D kind of goes into what other potential interpretations there are, a common one being an envelope. If the trajectory lies within, say, an envelope, it has to ride through. But per clause 7, the correct interpretation is to consider this as a voltage threshold versus time requirement. These time durations are cumulative over a 10-second moving window, except for this area above 1.05. That's going to be over a 3,600-second window. Another key note is for 500 kV connections, this continuous range from 1.05 to 1.1 is going to be infinite time. This whole row here is really goes back to the ANSI standards of how equipment is rated, and that's why it's different for 500 kV than say 230, 161, etc. Okay, so we know what the voltage thresholds and time durations are that the plant needs to ride through. The next question is, well, what does the IBR need to do when we're in either a continuous, a mandatory, or a permissive operating mode? And so those modes are formally defined in clause 3. And we're going to focus mostly on mandatory operation in this section. Continuous operation, I think of is kind of just the normal mode of operation. And there are some exceptions as you get closer to the lower voltage band here, specifically closer to 90%. Maybe you have to pick a priority to maintain both your active and reactive or voltage control objective. But for the most part, that's business as usual, normal operation. Permissive operation, on the other hand, is this section when the RPA voltage goes below 10%. And it's going to be, the requirement there is to either operate as if this is a mandatory operating mode region, or you can go into current blocking. If you go into current blocking, the caveat here is that you need to restart your current injection within 5 cycles of the RPA voltage getting back into the mandatory or continuous operating range. And so the next couple slides, I'll talk about this mandatory operating range. The first set of capabilities to consider here when the IBR is in the mandatory operating region, and this applies at the IBR unit level or the point of connection, is that the units need the ability to either operate in an active current or reactive current priority mode. And they need to be able to do either mode for either high or low voltage ride through. By default, the standard says reactive current priority. Additionally, we need to be able to set the level of reactive current injection per unit voltage deviation different for low voltage and high voltage ride through modes. So an easy example to think about is if they use a K factor type proportional control for voltage deviation, you may want to set that. The IBR unit needs the capability to set that differently for HVRT, high voltage ride through versus low voltage ride through. And finally, another very important point here is the IBR unit needs the capability to inject current to its maximum limit when it's in a mandatory operating region. The example I can think about that shows up is you prioritize reactive current. You meet the control objective for reactive current, but you drop your active current to 0. That's not what is required, and it's explicitly stated later in the standard. You want to be able to use the remaining current carrying capability up to the maximum limit. Okay, so that's the kind of the control, how you're going to set the control modes up on the front end. But then the question is, well, what do we do with that? So the first thing is, once the POM voltage goes outside of the continuous operating range, so you're in a ride through mode of operation, you need to maintain automatic voltage control. There's a couple footnotes related to K factor. One basically says that yes, K factor is automatic voltage control. It's closed loop control via proportional gain. And the other one says that K factor is not required. So you can use any control approach you want as long as you can meet the control objectives. Now the current injection, both the type, whether that's active or reactive, positive or negative sequence, and magnitude need to be dependent on the voltage deviation at the inverter terminal or the point of connection. We'll talk about that a little bit more on the next slide. Additionally, the current injection needs to be at the same fundamental frequency as the terminal voltage. And there's some exceptions for some of the off nominal frequencies that will show up during transients, severe faults, and those related to type 3 when it's either crowbarred or when you lose the rotor current. So it's kind of separated here into either balanced or unbalanced faults. So for balanced faults, the idea is that the IBR unit needs to inject an incremental reactive current in the positive sequence based on the POC voltage. And the incremental positive sequence reactive current, that's just going to be the difference between the fault, the reactive current during the fault, and the pre-fault reactive current output. Again, we'll see this show up in a couple different places, but any residual capacity, so any additional current carrying capability, once you prioritize reactive current, needs to be active current. So use the full current carrying capability of the IBR unit. And that's, of course, if you're in a reactive current priority. If it's active current, then it'll be the reverse. For unbalanced faults, now we have a deviation in positive sequence voltage as well as negative sequence voltage. So now we want to inject an incremental reactive current in the negative sequence that needs to lead the POC voltage. So it's going to be working to reduce the negative sequence voltage at the POC. And then if we reach the current limit, during these unbalanced faults, the preference is really an equal reduction of the incremental positive sequence reactive current and the incremental negative sequence reactive current. There's some other approaches that are okay per the standard, but in any of these approaches, we can't reduce the incremental positive sequence reactive current less than that of the negative sequence. Okay, so we've talked about what the type of current needs to be for a voltage deviation. So next is, well, how much current? And I think it's important to mention here that the standard is very intentional and even makes this top statement that it is not going to specify a universal magnitude here. And it talks about how that may be different for different interconnections, very different areas, etc. But what it does say is at a minimum capability, if the POC voltage goes below 0.5, the IBR unit needs the capability to inject either active or reactive current up to its maximum current rating. If the POC voltage goes above 1.15, it needs to absorb reactive current 30% of the maximum current rating. And then for unbalanced faults, if the POC voltage goes to 0.25 in the negative sequence, it needs the capability to inject negative sequence reactive current up to 50% of the maximum current rating. So there's a lot of words there. And again, I want to stress that K-factor proportional control is not required. But if you're familiar with it, this is essentially needs the capability to use a K-factor of 2. Okay, so we know the type of current. We know that the magnitude of current may be specific to a given interconnection. So here, the next part of the standard talks about the time domain response requirements of those current components. And those are summarized in table 13. There's a separate column for type 3 wind turbine generators versus full converters or all other IBR units. We can take the final column here as an example. So the step response time needs to be less than or equal to 2.5 cycles. So here in North America, about 41 milliseconds. Settling time less than or equal to 4 cycles. And so I've added the picture from some of the pre-phase material in the standard to give an idea that the step response time is the 0 to 90% time, and then the settling time is when you're in these two bands. Probably the important thing to keep in mind here is that everything we're specifying is in terms of phasor domain quantities, right? We're talking about sequence components, active and reactive. And so these times are inclusive of the DFT to get from the time domain to the phasor domain using a 1 cycle window moving of instantaneous data. So these times are inclusive of that. In the interest of time, I'll skip over the details on consecutive voltage ride through, but note that it's in this clause of the standard. So now we know what type of current we need to inject, how much, what the time domain response needs to look like. So once the disturbance is removed from the system, so the PON voltage goes back to the continuous operating region, the IBR plant needs the capability to restore active power at an average rate. And so if you work through all the math here, what it really winds up being is that this average rate of active power recovery is going to be configurable in this range from 0.1 per unit per second to 1 per unit per second. And the standard gives some tolerance to that. I think one key thing to keep in mind is this is not the requirement is not written as if you recover faster than this, you're fine. It needs to be at this average rate. It also talks about in this clause that any incremental reactive current that you injected during the low voltage ride through or high voltage ride through needs to cease or go back to pre-disturbance per our time domain requirements on the previous page. Or in table 13, I should say, 2 slides ago. Okay, so another requirement, so we're moving away from requirements based on fundamental frequency, line to line or line to ground voltage, and now we're going to look at the instantaneous values of the line to line or line to ground voltage. And this is the transient over voltage ride through requirement. So the standard talks about the original intent of this requirement is just to make sure that the IBR plant does not trip for normal switching events on the transmission system. The reference point of applicability is the point of measurement. So there's some coordination that needs to be done to make sure that the IBR units can actually ride through what shows up at the POM. But assuming that we're still in a ride through mode of operation or a continuous mode of operation for our phasor domain voltages, the requirement here is based on the instantaneous phase to phase or phase to ground magnitudes do not exceed these thresholds in table 14 for this time duration in the next column. And pictorially, it looks like this chart here in figure 11. A couple key notes that this is cumulative over a 1 minute window. And there's a footnote in the standard that gives an illustration of what that looks like. So you're going to have the thresholds on both the positive and negative side of the waveform. So anytime it goes over the threshold, you can add that time up to see if you're in a ride through, must ride through, or if you're in a may ride through or may trip area. Other important note is current blocking is permitted once the POM instantaneous voltage goes over 1.2 per unit. However, you need to start current injection within 5 cycles of that voltage going back down below 1.2 and staying below 1.2. So finally, so that was probably the majority of the detail in this section. There's also frequency ride through requirements in clause 7.3. This is the table here. They're all in based on whatever the nominal frequency is. So I've superimposed what it looks like for a 60 hertz system here in red. The key thing is this is cumulative over a 10-minute window, and there are some exceptions for volts per hertz capability of the IBR plant equipment. And this really goes back to, you have type 3 wind that's directly connected to the AC system. You have transformers, etc., that may have volts per hertz limitations. So the standard's not requiring you to exceed that of normal equipment design standards. When you're in a mandatory operating mode or the continuous, what the IBR needs to do is really reference back to clause 6, which is the primary frequency response and fast frequency response requirements. And note that fast frequency response right now is only applicable for under frequency conditions, but all of the frequency response performance is specified in clause 6. So final 2 requirements that were lumped under the frequency section, one being the rate of change of frequency. So the IBR plant needs to be able to ride through rate of change of frequency up to 5 hertz per second, assuming that the frequencies in the mandatory or continuous operating region. A key note here is how that's calculated. So we need an averaging window of at least 0.1 seconds. So can't take 2 samples very quickly, divide it by a small amount of time and say that rate of change of frequency is greater than this, therefore I don't have to ride through. It needs to be averaged over this 0.1 second window. And then finally, there's a phase angle change requirement. And the key here is that as long as a positive sequence phase angle change or phase angle jump is less than or equal to 25 degrees, the IBR needs to ride through. And so that means that if during, say, an unbalanced fault, some of the individual phase angles change, the plant needs to ride through, provided that the positive sequence phase angle change is less than or equal to 25 degrees. Now, when there's a phase angle change, there's probably going to be active and reactive current changes and from the IBR. And so the requirement is for those to be positively damped. So yeah, that's my last slide. Julia, I'll turn it back over to you.
Thanks, Wes. Excellent presentation. Very good detail and timing too. All right, so we'll move on to Jens now to talk about PRC 29 and comparison with 2800 requirements that you just heard about from Wes. Jens, before you get started, I just wanted to remind people to please go to slido.com, use i2x first 2 as a code and indicate what sector they are representing. We have 150 people on the call. There are 66 indications so far. It would be really great to get a feel of the audience here. So I'll leave it open for another maybe 5-7 minutes while Jens is presenting. Go ahead, Jens.
Yeah, thank you so much. Just doing quick sound check. You can hear me, right?
I can hear you.
Okay, thank you. So yeah, thank you so much. I think if we have learned one thing from Wes's presentation is that details really matter when it comes to these technical requirements. And I think it's very encouraging to see how IBR developer is really aware of all those details. So my task is to provide you with a much more higher level presentation. This will be a comparison of write-through requirements in the most recent draft NERC PRC 29 with IEEE 2800 2022 write-through requirements that were presented by Wes. I would like to acknowledge my colleagues, including Manish Patel, who has been following the NERC standards drafting team very closely and has helped put together this presentation. So just for context, you're probably all aware of FERC Order 901, which is about reliability standards to address inverter-based resources. This order went into effect in December last year. And then in January, NERC published a work plan, which includes 3 important milestones. One in November this year, where NERC intends to file IBR performance requirements standards, as well as disturbance monitoring standards and standards for post-event performance validation. In 2025, NERC intends to file standards for data sharing, data and model validation, and performance-based validation. And then in 2026, they are planning to file standards for planning and operational studies as it relates to inverter-based resources. This is a very ambitious 3-year timeline, and NERC is required to fulfill this timeline based on the FERC order. In its order, FERC acknowledged the potential value of IEEE 2800 requirements and the forthcoming planned conformity assessment per the currently drafted 2800.2. And they declined to incorporate these IEEE standards by reference into their order. That said, both standards could inform requirements for various items in this FERC order, including the performance requirements and specifically the write-through. That said, however, NERC did mention that they cannot refer to IEEE or other industry standards by reference. So which standards are addressed in this order? It's about a dozen or so, or even more standards that are either going to be developed or revised based on Order 901. Today, we will focus only on PRC 29 as one of the PRC family standards. In addition to that, the FAC standards for facility interconnection requirements and studies are impacted, as well as the MOD standards and TPL, TOP, and IRO. And you see how the milestones of each of those, the milestones of the FERC order and NERC plan relate to these standards. So that puts it into a timeline. So let's jump into the PRC 29. EPRI and many other industry entities submitted comments on the very first draft of PRC 29 back in April. Our comments are based on our research, and we took the time to really go through line by line of the draft PRC 29 in order to understand, first of all, what requirements are proposed. Are these requirements well defined? Are the terms that are used well defined? And how do those requirements relate to or compare with IEEE 2800, which at this point is just a voluntary industry standard, but probably one of the more authoritative references, given the broad consensus that went into the detailed requirements that are codified in IEEE 2800. That said, IEEE 2800 is not the only, and we would never call it the best reference standard. As a matter of fact, IEEE 2800 is just the very first voluntary IEEE standard that can help inform and support more reliable interconnection of inverter-based resources to the grid. There may be other standards, and also 2800 is only a technical minimum standard, so it might not be sufficient in all situations or for all regions, which means regions can certainly go above and beyond IEEE 2800 requirements. At the same time, we are learning as various regions are adopting the standard that some of the requirements, even though agreed to through the IEEE open consensus development process, can actually be challenging to apply to particularly legacy IVRs, but some requirements might also be challenging to apply or even verify for new IVR plans. So we provided these detailed comments, and we interacted with the standard drafting team to help further explain some of our comments where there were questions. And we really, really appreciated the interaction with the standard drafting team that has developed the NERC PRC 21 draft. So let's start at a high level. First of all, we need to remind us what reliability requirements can NERC, as the North American Electric Reliability Corporation, develop in their reliability standards. In many cases, we are used to one category of requirements. Those are the so-called performance-based requirements. Performance-based requirements define a specific reliability objective or outcome achieved by one or more entities. It can be measured using system data or trends, and has four components: who does what, under what conditions, what shall be the action to achieve the particular outcome. But that is not the only type of reliability requirement that NERC can develop. And if you want to know more about it, you can refer to the NERC Rules of Procedures, which were last updated in November last year. Other requirements include risk-based requirements that define actions, and also capability-based requirements. And capability-based requirements define capabilities that are needed by one or more entities to perform reliability functions that can be measured by demonstrating that the capability actually exists. And they are often framed as who, under what conditions, shall have what capability to achieve that particular outcome. What's important to note is that this most recent draft of PRC 29 now includes capability-based requirements. And really what that comes down to is that it prescribes what level of technology capability should be aimed for. So it's almost like the choice if you want to move around town, whether you go for the horse carriage, the medium-sized car, or the sports car. And this is very much aligned with the approach that IEEE 2800 and other performance-based and minimum capability IEEE standards have chosen. It also comes with some challenges related to how to actually verify these requirements. So let's move forward and look at some example details. We will not have the time to go into all of those details, but on the first slide, we will review missing or insufficient or questionable requirements and possible remedies in the most recent draft of PRC 29. In the next slide, we will look at internal inconsistencies that we still see in the draft. And that draft was published, I think, on Tuesday last week. And then on the third slide, we will highlight specific areas where the current draft appears to conflict or go far beyond the IEEE 2800 requirements. So let's pick a few examples here. In general, the applicability of requirements in 2800 is specified with some limitations for the grid conditions. There are exceptions that are permitted to allow IVRs to diverge from their write-through when grid conditions are outside normal conditions that would be specified by the transmission operator. So those could be certain extreme contingencies, and the standard does not go as far as defining what the threshold for extreme contingencies are under which the standard requirements may not apply anymore. But it does recognize that if you are in a contingency, maybe n-1 or n-x, you may not have the ability with that plan to stay connected. NERC PRC 29 in its latest draft currently does not include such limitations. The write-through definitions seem to be different between NERC PRC 29 draft and the published IEEE standard. When it comes to voltage write-through capability, 2800 allows for an exception for self-protection when negative sequence voltage is greater than specified duration and threshold, whereas PRC 29 does not allow for that exception. Also in the write-through capability continuous operation region, 2800 specifies certain requirements as cumulative, whereas PRC 29 remains silent on those details. And let's look at the next category, which are some internal inconsistencies and possible remedies. So one inconsistency is that there may be some unintentional inconsistencies in various terminology within the latest draft PRC 29 compared to the same terms specified in IEEE 2800. We do recommend to use consistent terminology to avoid any unintentional conflicts. For voltage write-through, some of the performance requirements is included in the draft PRC 29, And these seem to be well aligned with IEEE2800, but more thorough review is necessary once the next draft is posted. However, the draft PRC does not specify any requirements when frequency is within continuous or mandatory operation region. This approach is acceptable from our review because it would allow the transmission planner to then specify, for example, frequency response during a normal operation. But here are some possible conflicts that we would like to highlight. One is that there may be these unintentional conflicts through misalignment of terminology in draft PRC 29 and 2800. And probably the most prominent one is that the draft PRC 29 goes over and beyond the frequency write-through capability requirements as they are specified in IEEE 2800. The draft PRC has more stringent frequency write-through requirements, and those are aligned with what appears to be specific regions requirement, which have not found the consensus in IEEE 2800 as technical minimum requirements. So the question that comes up is, does a NERC reliability standard have to adopt the most stringent frequency write-through requirement, or could selected regions go above and beyond a NERC requirement? Also, we identified a lack of exceptions for the volts per hertz limit. Potentially, that could be a problem for type 3 wind turbine generators and transformers. And this is where some of the details that are considered in IEEE 2800 could matter. And we encourage the standard drafting team to further consider some of those matters. And last, we identified a more stringent 15-minute time period for the cumulative specification of frequency write-through. So summing this all up, what we would like to convey is that it's important to recognize that the new draft PRC 29 includes capability-based requirements. That seems to be a significant alignment with IEEE 2800 and other capability and performance standards. It also could bring some challenges in how to verify compliance, specifically how the design of an IBR plant could be assessed prior to that IBR plant's commercial operation date. We believe that this is a good approach because by the time an IBR plant enters commercial operation, it is often too late to make any design changes. And if the equipment that had been used in the plant does not have those capabilities, it may not have them during its lifetime. So looking into that during the design stage of the plant does seem to be like an important consideration. Now, we really only presented a high-level comparison here. Much more thorough comparison will be done when the next round of ballot opens. Currently, the draft is under ballot, and we do encourage everyone to go to the NERC website and review the draft, provide their comments, and if applicable, cast their vote. And we do hope that some of the remaining inconsistencies, specifically due to the use of wording, will resolve over time as this draft develops further. All that said, we do like to acknowledge that IEEE 2800 has many more requirements that we have not addressed in this review at all. So they have not been in the focus. And going forward, we encourage the stakeholders and standard drafting team to adopt language that at least aligns with IEEE 2822, considering that direct reference does not seem to be an option. And that's my last slide, and I'll hand it back over to you, Julia. Thank you so much.
Thank you, Jens. Thanks so much. So before we go to Megan, and it's maybe suitable right now, I'll close the poll for asking people what industry sector they're from. We still got maybe about 50% of respondents, but that's all right. But now, as Megan talks about MISO's adoption of 2800, we would also like to poll people if they're interested to hear more about adoption efforts in other regions and have a meeting dedicated just to that. So I'll open that poll, and in the meantime, Megan, go ahead and get started. The floor is yours.
Sounds good. Quick mic check as I pull up my slides. Can everyone hear me okay?
Yeah.
Great. Okay. Good morning, everyone. My name is Megan Pamprin. I'm an engineer with the Strategic Assessments team at MISO, and today I'll be presenting on the first round of IEEE 2800 adoption that we did at MISO. First, just briefly some background about MISO. You can see our footprint on the map there. The generation mix for our footprint is largely coal and gas at this point. As of the end of 2023, about 16% of our installed capacity was wind, so that's about 30 gigawatts, and then 4% was solar, so that's about 7 gigawatts. And there was pretty much, no substantial battery capacity on the system as of the end of last year. So our IVR penetration is relatively low at this point, but that's expected to change pretty rapidly. And we've started to see that large change in our interconnection requests, starting with our 2022 interconnection queue. That's shown on the left there. It set records for not only the total capacity in the queue, which was 170 gigawatts, but also just with the amount of inverter-based resources, and those made up over 95% of the requests. We saw a similar story in the 2023 interconnection queue as shown on the right. Of course, not all of these projects will get built. This is just the amount entering our interconnection queue, but it does show the opportunity that we have at MISO to define some requirements ahead of this coming influx of IBRs. Another driving factor for IBR performance requirement adoption was the series of NERC disturbance reports, which document IBR performance issues across the US going back to around 2016 or so. We've been closely tracking these events as they've continued to pop up in different regions and involve different types of IBRs. And one of the main lessons learned is that some of the performance issues that led to these events can be prevented through implementation of standardized requirements. So given the need to define IBR performance requirements and the timely publication of IEEE 2800, MISO launched our adoption effort in 2022. So here I have the timeline overview of the work that we've done to date. In 2022, that's when IEEE 2800 was published, and we began work shortly after that to understand the requirements in the standard. We completed a gaps analysis at the end of 2022 to see which parts of the standard MISO did not already require of IBRs. Then at the beginning of 2023, we brought this topic of 2800 adoption to one of our stakeholder forums to present details to stakeholders and get their feedback. In February of 2023, we completed a prioritization of 2800 requirements. And so rather than adopting the whole standard at once, we selected the highest priority requirements to propose to our stakeholders for initial adoption. And so we'll discuss which ones had highest priority a bit later in the presentation. The culmination of this work was changes to MISO's tariff, specifically our generator interconnection agreement. And we filed these tariff changes with FERC in February of this year, and FERC did recently approve them. So now that we have that overview of the work from last year, we can dive into some of the details. I know I mentioned our gaps analysis. We followed a typical gaps analysis approach in comparing the 2800 standard against MISO's generator interconnection agreement language. And the nature of the gaps varied from a requirement being missing in MISO's GIA, partially defined in the GIA, or defined with different parameters, and those were all kind of classified as a gap. So from this analysis, we identified 21 requirements from the standard where there was a gap in our current GIA requirements. And so they fell into the four main categories you can see here: general, monitoring and control, voltage support, and then dynamic response and reliability services. That category kind of encompasses all of the ride-through requirements in 2800. So there were a lot of gaps identified, and as we've already heard from Wes's presentation, the clauses in the 2800 standard do have a lot of complexity. So instead of trying to adopt them all at once, we decided to do this over multiple phases. So it was necessary to prioritize which capabilities should be in each phase. Really wanting to emphasize reliability as we did this, we used the NERC disturbance reports as our primary source for prioritizing which 2800 requirements to adopt first. And to do that, we mapped the inverter loss of generation cause codes for each event to the 2800 requirement that could have prevented or maybe addressed that issue. We also considered potential future grid needs through 3 other prioritization sources, including the FERC IBR NOPR, which led to Order 901. And on the far right-hand side of the table here, you can see the resulting priority of each capability based on all 4 of our prioritization sources and dynamic responses. Specifically, most of the ride-through capabilities bubbled up to the highest priority, as shown in red there. So using that prioritization as a kind of a basis, and after hearing from stakeholders about what they considered to be high priority, we developed these 3 phases for IBR requirement adoption. So phase 1 is what we worked through in 2023, and that really focuses on ride-through requirements. And so I'll share the details on exactly which 2800 clauses this encompasses in a few slides. Phase 2 requires core system support functions for IBRs related to reactive power support and primary frequency response. And phase 2 is what we are targeting for implementation in 2024. So we're actually going through the stakeholder process with those now. And then lastly, phase 3 is more advanced system support requirements, things like fast frequency responses. So as we've gone through the stakeholder process, some of these have shifted a bit, but the overall intent of these 3 phases has mostly stayed the same. So given all that background, here is the summary of where we landed for the first round of IEEE 2800 adoption. The requirements that we implemented were from 3 main sections of the standard. The first was clause 4, which is like the general clause. From there, we included the subclauses that detail reference point of applicability and applicable voltage and frequency, as both of those contain pretty essential definitions and details that the rest of the standard does rely on. We also included the subclause on measurement accuracy. And the thinking there was that if we do want to implement ride-through requirements, the IBR plant should have good measurement accuracy. Otherwise, those ride-through requirements and associated protection settings won't be effective if the plant is taking in bad voltage or frequency measurements. And then the last part of clause 4 we adopted was the section on return to service and enter service. And so that's where we could specify things like duration of the enter service period and some other details. So the rest of the requirements were from clause 7, which of course is our main topic of discussion today. So from subclause 7.2, we implemented requirements for voltage and transient overvoltage ride-through, as well as the requirements for current injection during voltage ride-through, and then restoration of active power output after voltage ride-through. And then lastly, from clause 7.3, we pulled the requirements for frequency, Rokoff, and phase angle jump ride-through. As discussed before, these requirements were incorporated into MISO's Generator Interconnection Agreement, or GIA. And so the new GIA language, after working with stakeholders to refine it last year, as I mentioned, was filed with FERC in February of this year, and FERC did approve it, so the requirements are in effect. As far as which IBR plants these requirements apply to, we are not doing retroactive application of any kind. The requirements will apply only to IBRs coming out of the 2022 interconnection queue or later. So they will not apply to any existing plants or even to any projects coming out of earlier queue cycles. And just to give you a better sense of the timeline there, the projects in the 2022 queue cycle will probably go into operation around the end of 2026 or so. So that's when we'll start seeing IBR plants come online that meet these requirements. So now that we've talked about what we did adopt in the first round of 2800 implementation, let's talk about what we didn't adopt from clause 7. So we excluded oh yes, please.
Would you please, there is this sharing bar that shows if you press on hide there, it will disappear. Thanks. Because it
Thank you
covers.
so much. Sorry about that, everyone.
No worries.
Great, thanks. So we excluded subclauses 7.2.1 and 7.3.1 from our adoption because we determined that the protection items were kind of out of scope for MISO. Additionally, we did not adopt the consecutive voltage deviation ride-through requirements in this first phase. And this decision was made based on stakeholder feedback that we received and information from OEMs that we gathered through outreach and through attending industry forums, saying that this was one of the more challenging requirements to fully understand and ensure inverter compatibility with. Just to note, though, we have actually included this in our second phase of 2800 adoption, which is underway now, as I mentioned, just because the second phase requirements will be adopted and effective later than this first round. And we've gotten some information from OEMs about when inverters that are compatible with this consecutive voltage deviation ride-through requirement will be available. So we followed the detailed reference approach to implement the requirements, which means that for the most part, we tried to just reference the 2800 clause we were adopting and did not really rewrite anything in our own words. We decided to add the new requirements, as I mentioned, into the generator interconnection agreement portion of MISO's tariff, which is where the previous IBR requirements were already located. So I have an excerpt of the tariff language here on the slide, specifically for clause 7. First, we simply specify which clauses are to be adopted, and then we note any exceptions, which here are those 3 subclauses that we just reviewed that were not adopted from clause 7. Then following that, we address any decision points that were left open in the standard or, add additional clarification as needed. An example of one of those is included in the screenshot here, but there are a few more than that. So we'll go over all those in the next slide. And then lastly, we included a summary table just to provide as much clarity as possible about which subclauses were adopted. So this is the summary of all the additional detail we added into the tariff language for adoption of clause 7 specifically. We made clarifications on kind of 3 main items and then addressed 2 open decision points. So starting quickly just with the clarifications, for voltage ride-through, we clarified that the TO or transmission owner may need to specify what the nominal voltage is if it is not one of the standard voltages in the ANSI standard. Also for voltage ride-through, we made a clarification, basically just reiterating that we want all IBR plants to be in reactive power priority mode by default, as is already stated in the standard. And then the main clarification here is that we point to a place in MISO's GIA where it could be stated if the IBR plant is to instead operate in active power priority mode. And then lastly, and this one is a bit more of a modification, in the frequency ride-through part of clause 7, specifically, and if you're curious, subclause 7.3.2.3, there are a few references to clause 6.1 of 2800, which I know Wes mentioned, and that's the clause that covers primary frequency response. We did not include clause 6, in our first round of 2800 adoption. So we stated in our tariff language that any references to clause 6.1 should instead be replaced by references to the primary frequency response language that already existed in MISO's GIA. But just a note that we will actually be removing that language from the tariff once we adopt clause 6.1, and that's coming in our second phase of 2800 adoption, which is underway now. So we're definitely striving to align with 2800 language, and we'll be cleaning that part up as soon as we can. Okay, and now we can take a look just quickly at the two decision points that were left open in the standard that we had to address in our tariff language. The first was for the section on voltage disturbances in the continuous operation region. So the standard states that if the plant can't deliver both active and reactive power during a disturbance in that continuous operation region, then the TS operator needs to state whether preference should be given to active or reactive power. And so in our tariff language, we specify that preference should be given to reactive power in that case. And then the second decision point was for the subclause that covers current injection during ride-through mode. As Wes mentioned, the standard does not specify the magnitude of incremental, positive or negative sequence reactive current injection that is required during a fault. But what the standard does say is that the TS owner should consider specifying that based on system needs. So what we did is in our tariff language require the interconnection customer just to submit information on the plant's default relationship between incremental reactive current and voltage change. And then the language states that, MISO or the transmission owner can specify a required relationship that's different than that default if necessary. Okay, and that covers all the extra tariff language. So we really tried not to modify any 2800 language except for that specific case where we altered the reference to clause 6.1. Okay, and I want to take the next two slides just to cover some major points of feedback we received from stakeholders during our implementation of this first phase of requirements. So this first point isn't directly from clause 7. Reference point of applicability is actually covered in clause 4, but of course most of the clause 7 requirements are expected to be met at the RPA, as Wes mentioned, so it does have impacts to clause 7. MISO considered both the point of measurement and the point of interconnection as possible locations for the RPA. We proposed the POI actually initially because we saw it as the best reliability supporting solution from the transmission system perspective to include that IBR tie line there. But we received some substantial stakeholder feedback pushing for the POM instead, just because it aligns with current standard compliance practices. For example, PRC 24 requirements apply at the POM. So we agreed with the points that stakeholders made and saw POM as an acceptable RPA. That's also the default in 2800. And so we moved forward with that. Okay, and then additional stakeholder feedback we received was around our implementation timeline. Initially, we proposed to apply these requirements to IBR plants coming out of the 2022 interconnection queue without exceptions. We did get some feedback from stakeholders that some sort of flexibility was preferred, and it varied by OEM, but there were some requirements for clause 7 that, that it was possible that current technology could not meet. They were still evaluating it. They had work underway to make sure that new inverters could meet the requirements as well. So we implemented an exception process where any projects in the DPP 2022 cycle that execute a generator interconnection agreement before January 1st, 2025 can submit OEM documented exceptions to the requirements. However, there have been some shifts in our interconnection queue study process, so it's not likely that any of the DPP 2022 projects will actually have GIAs signed by January 1st. But we are not considering moving the exception date back at this time because that date was determined based on when OEMs communicated that they could have compatible inverters available. Okay. Thinking ahead to next steps, we do see development of conformity assessment procedures as a key next step in this entire process. Up to this point, we've really focused our efforts on working through, our stakeholder process and implementing the requirement language through tariff changes. But thinking ahead, we definitely understand the need for test and verification procedures as outlined in IEEE 2800 and as under development in the P2800.2 standard. So here I have the outline of the different test and verification steps in 2800. All of these steps would involve many different stakeholders, so it will take a lot of coordination to develop this process effectively. We're trying to track the development of P2800.2 and would like to take steps towards, developing conformity assessment procedures at MISO in the near future. Okay, wrapping up with final next steps here. We are closely following the ongoing development of NERC standards, especially those that have overlap with 2800 requirements like PRC 29, as Jens talked about today. And we're submitting comments where we can, asking for alignment between the two as much as possible. And then I know I've mentioned this a couple times, but we're also finalizing that second phase of 2800 adoption, hoping to finish up all our new tariff language by the end of this year, and then filing with FERC after that. Okay, so that's my last slide, and I think I'll hand it back to Julia for Q&A.
All right, thanks so much, Megan, and we'll probably have you over once the phase 2 is complete. Thanks so much for taking time and coming here. We'll take some time for Q&A. There are some questions that came through audience Q&A in Slido. And again, I encourage people to participate in the poll that is open in Slido and post the audience questions as well. We'll take some now. Some of the questions are kind of related to discussion items we have later, so I'll leave it till that time. And then also, if we don't get to some specific questions on details of write-through, I have a open question at the end of this meeting, and you can post it there. We'll make sure that all of the detailed questions about VRT and other write-through requirements are addressed offline. So, because I think it's very important that people on the call at least understand all the details.
Julia,
all right, so
quickly,
let's start with first question. I think.
I stopped recording now, correct?
Yes. Yes, you stop recording now. That's right.